Last week we talked about the different types of compounds. We had ionic and molecular compounds. This week we're going to start looking at what holds those compounds together, and those are chemical bonds. So a chemical bond is the force of attraction that holds a molecule or a compound together. And there are two types of chemical bonds that we're going to talk about. First is ionic bonds, and the second is covalent bonds. Here we have calcium carbonate. If you remember from last week, it's because there's a metal, it's an ionic compound. Ionic compounds always have ionic bonds. This is CO2. This was a molecular compound. Molecular compounds are always held together by covalent bonds. So the key, again, is to look for a metal. If there's a metal, it's an ionic bond. If there are no metals, it's a covalent bond. So an ionic bond is a case where you have different charges, and different charges attract each other. You know that positive and negatives attract. That's exactly what an ionic bond is. In our sodium chloride, we have positive sodium, negative chloride. They're attracted to each other. In a molecular compound, we don't have charges. Instead of being held together by charges, they're held together by the fact that they are sharing an electron, and we'll see what I mean by that. So in the ionic bond, we have this electrostatic attraction, big word, not a complex idea. Negative attract positive, opposites attract. So in our ionic compound, here we have our greens and our yellows. Let's say the green is our sodium, yellow is our chloride. The negatives attract the positives, and of course the things that have the same charge, in this case I think I said the yellow is the chlorine, the negative is going to repel the negative. And this always happens between a metal and a nonmetal. And that's because metals form positive ions and nonmetals form negative ions. In this case, the electron is actually transferred. It's transferred from the cation, which is the metal, to the anion, which is the negative nonmetal. It's transferred meaning it's no longer with the cation, it completely goes over to the anion. And we'll see how that's different in a covalent bond. Ionic bonds are extremely strong. That cation that gave up the electron doesn't want to leave it. It didn't want it to begin with, but it also doesn't want to leave it once it gave it over to the nonmetal. A covalent bond is a sharing of electrons. It's not a matter of the cation saying, I don't want the electron, you take it. Instead, it's a matter of the one atom realizing that we can both be happier if we both share this electron that I have. So covalent bonds is always between nonmetals. Like I said, look for a metal. If there's a metal, it's ionic. If it's just nonmetals, it's covalent. And the electron is not transferred. Both atoms are holding on to it. And we'll see this later on, but these sharing electrons usually happen in pairs. Covalent bonds are strong, don't get me wrong, but a covalent bond is slightly weaker than an ionic bond. So what we're going to do is, when I tell you to, you'll pause the video, take a look at these compounds, and try to predict whether they're going to have ionic bonding or covalent bonding. So go ahead and pause it right now. Okay, so let's look at number one. Just like we did last week, the key, look for a metal. Is there a metal in this? Sodium fluoride. Yes, there is. Sodium is a metal, so this has to be ionic. ClO2. These are all nonmetals, covalent. Iron is a metal, ionic. SO2. They're all nonmetals, so that's covalent. This one's a little bit trickier. there is calcium. Calcium is a metal, so there is definitely ionic bonding. But if we look at just this part of it, ClO2, those are nonmetals bound to nonmetals. So there's covalent bonding in here, but then there's also ionic bonding with the whole thing. So I hope you can see that, but this is a little more complicated than you would be expected to do on a quiz or an exam. So there are our answers. That's so that you have them. We can break these down a little bit further. An ionic bond is an ionic bond. You can't break that down further. But covalent bonds, there are polar covalent bonds and there are nonpolar covalent bonds. A polar covalent bond is a case where the electron isn't shared equally. One of the atoms holds it closer to it than it is to the other partner. And this only happens if the two atoms that are sharing the electron are of different elements. If you have two of the same element, it won't be a polar covalent bond. And that's because different elements have different electronegativities. And electronegativities is going to be on one of the slides coming up, so don't worry about that at this point. A nonpolar covalent bond is when we have equal sharing of the electrons. The electron is right in between them. It spends the same amount of time with either of them. And this only happens between atoms of the same element, with the one exception of carbon and hydrogen. So if we said that the polar covalent bond forms because they have different electronegativities, all elements have different electronegativities that you'll see later. So the only way to have the same electronegativity on two atoms is if they're the same element. So a polar covalent bond is slightly stronger than a nonpolar covalent bond because a polar covalent bond is a little more like an ionic bond. Nonpolar bonds are weaker, and this polarity happens in polar covalent molecules. What I mean by that is that when you have a molecule that has a polar covalent bond, the electrons spend more time in one area than another. And because the electron is negative, that creates an overall charge difference on one side of the molecule versus another. So if you want to classify our bonding, you can use this flowchart. Is it ionic? Is it covalent? If it's covalent, is it polar or nonpolar? Let's go back up. Look at your compound. Is there a metal? If there's a metal, it's ionic. If there's no metal, it's all nonmetals, it's covalent. Then look at the elements. If everything is the same element, or carbon and hydrogen, it's nonpolar. If there's more than one element, at least two different elements, it's polar. So let's look more at these polar covalent bonds. I said it's not shared equally. So here we have a fluorine and a hydrogen. The fluorine holds that electron closer to it than the hydrogen does. And because the electron is negative, the fluorine gets this partial negative. This little symbol here is a lowercase delta. And so we write partial negative as a lowercase delta negative. And so because the hydrogen has less electron than the fluorine, it has a partial positive. There's always going to be a partial positive to balance out a partial negative. So here is that electronegativity. Electronegativity is how strong an atom is able to hold an electron. It's how attracted it is to that electron, how close it wants to keep it to itself. So if you have two atoms, they form a covalent bond, and they have a difference in electronegativity. That means you're going to get a polar covalent bond As we already said, polar covalent bonds are more like ionic bonds, and so that makes stronger bonds. If you have no difference in electronegativity between your atoms, it's a non-polar covalent bond. So we actually have electronegativity scale, where every element is assigned electronegativity. And so what we can do is we can simply look at that chart and look up the electronegativity on two different elements and look at the difference between those electronegativities. The element that has the higher electronegativity is the one that has the stronger pull. So the one that has the stronger electronegativity, the higher electronegativity, is the one that will have the partial negative. The one with the lower electronegativity will have the partial positive. That is always the case. So this is that chart. It's actually, in this case, drawn out just like our periodic table. And so we have our atomic symbol, there's fluorine, and then underneath, in this case, that number is the electronegativity. So you see fluorine here has a 4.0, francium down here is 0.7. General trend, what you have to remember is that fluorine in the top right corner is the most electronegative. So as you go from left to right, electronegativity goes up, it gets stronger. As you go from the top to the bottom, electronegativity gets weaker, the number goes down. If you can't remember those trends, all you have to remember is that fluorine is the most electronegative element. That's how I remember it. If you can remember that, you can figure out the trends from there. So again, take a second when I say pause the video, try to figure out which element in these compounds is going to have the partial positive, which one will have the partial negative. So go ahead and pause it. Okay, so what we have to do is we have to find both elements on the periodic table and just figure out which one has the higher electronegativity. So here we have SO2. Let's go back to our chart. We have S, we have O. O, oxygen, has a higher electronegativity, so it has the partial negative. Sulfur has the partial positive. Here we have N2. In this case, because they're both nitrogen, they both have the same exact electronegativity, and so there will be no partial charge. This is a non-polar covalent bond. Is H2S. We go back. Sulfur is 2.6. Hydrogen is 2.2. Sulfur is higher. Sulfur is partial negative. With CCl4. Here's carbon 2.6. Chlorine 3.2. Chlorine is partial negative. And then O3, just like with N2, this is a non-polar covalent bond. There are no partial positives, there are no partial negatives. So that's what I wanted you to know before you came to class today with bonds. We'll talk about the rest in class. I'll see you then.